Welcome to the fourth and final video in my series on multimodal embeddings. In this video, we'll look at a dataset where CLIP has little semantic understanding and performs classification poorly. Then we'll fine-tune CLIP using PyTorch in order to achieve a model that performs classification on this dataset of images extremely well. I'm Alex and I'm a data engineer, and here on ZazenCodes, I teach full-stack data science. In order to support the channel, you can check out my premium content over on Patreon, and you can sign up for free for my weekly newsletter. The fact that we're ending this video series with fine-tuning is perfect in my opinion, because we've pushed CLIP as far as it can go for generating a semantic understanding of images, text, even audio earlier in this series, and now we need to fine-tune it on some data set that's out of its semantic understanding to adapt CLIP for our specialized use case. Part of what makes machine learning so beautiful and interesting to me are all of the different real-world use cases. If you let me know what you're working on, I would be grateful for that. Here's some use cases that I thought of for fine-tuning an embedding model like CLIP. For medical imaging, it could be used to identify diseases or anomalies in medical scans. For agriculture, it could be used to monitor crop health or identify pests or diseases. For manufacturing, it could be used for quality control and detecting defects in products. And for satellite monitoring, it can be used to analyze images, track environmental changes or urban developments, or even something like supply of certain goods that you can see through satellite images. And in fact, the satellite image problem is what we're tackling today. We'll be looking at a data set of over 1,000 labeled satellite images, where land has been partially flooded. So in some images, the land is totally normal and there's no indication of flooding, and other images have labeled parts that have been flooded. And we're going to reduce this to a really simple binary classification problem where we're saying, is this image flooded or is this image not flooded? So we could take data that's unlabeled and get our model to tell us if we're looking at an image that has some area of land that's been flooded or not. This is not something that CLIP is very good at. We achieve about 70% accuracy, but after fine-tuning, we achieve a much greater accuracy on this classification task. Here's how this will work. The first thing I'm going to do is look at each image and generate a list of strings for the caption of that image so that we can train CLIP to associate the embedding of the image with the embedding of the caption. And the exact captions I'm going to be using are a satellite image of a flooded area of land and a satellite image of a non-flooded area of land. During evaluation, we'll feed the model a bunch of images and use the cosine similarity to compare the embedding of that image with the embedding of those text labels that I just mentioned. And the label with the biggest score will be assigned to that image. Then we'll be able to use the ground truth labels to determine the accuracy. During the training, we're going to be using this information to optimize the parameters of CLIP to best suit this problem, to be able to achieve this classification properly. CLIP has something like 150 million parameters, and we're going to be adjusting these using the atom optimization method, which is similar to gradient descent, in order to achieve parameters that work exceptionally well for our particular problem. In doing so, we're probably destroying the effectiveness of CLIP on any other use case. After fine-tuning, we'll save the model to the disk so that we persist it. And finally, we'll perform evaluation with the fine-tuned model. I've got a test set of data that I've withheld from the training, and I'm going to see how well our model performs on that test set of data. And of course, at the end, I will finish with a few MLOps considerations. So hang around until the end of this video to hear about those. This is the most exciting demo I think we have in this series, even though there's been some really great ones, so let's get into it. You can find this code on my GitHub. I've got a link here called Multimodal Embedding Series, which you can follow. It just goes into this source folder, and this is all the source code for this inside of my notebooks folder. I've got all the Jupyter notebooks that we've been using, clone this entire repository in order to get access to that. So I'll grab the HTTPS URL, and then I'll go over to my terminal and I'll say git clone, and I can paste that in, go into it, ZazenCodes YouTube, and then go into the source folder and multimodal embeddings, and that's where all of this code is for this project. And the first thing we want to do is set up a virtual environment for these requirements. Now, I've already done that, but if you haven't, you can say python-m venv and create that virtual environment. Then you can say venv bin pip install -r and install that requirements.txt. That's all of these ones right up here. Some of these you don't actually need, like the memory profiler. So if these are giving you problems, consider just installing them one at a time as they come up in our notebook. And you'll see that in the demo today. So you can go ahead and install this. I'll just run that anyway. It's all going to be okay. I'm using Visual Studio Code, VS Code, for this because I find it gives me a really good Jupyter Notebook experience, and it's nice and dark, which is great for screen sharing. But when we run this for the first time, it'll ask us to select our virtual environment. And I just want to make sure I'm picking this one, venv, right here. Now let's look at our data set. Here it is on GitHub. There's a link to Dropbox that actually has this data. Click on this link here and download the right data that you need. So on my system, I put this in a folder called FloodNet. And inside of here, I have those two folders, which we were just looking at on Dropbox. Look at this training set. We're going to load those up. And then later, I'm going to be using test data when I want to actually see how well our fine-tuning worked. Start by loading a bunch of images. Path, we can see what these look like. I'll import display my image.open. This will be our first image. So here, to me, it looks like we have some flooding, but I'm not actually exactly sure the label for this. We'd need to look in these color masks. So here is where our color mask data lives. Color masks train set. So this is the label that I want. And so I can plug that in, display this image.open. So this is all blue, which means something. If I go over to this color palette values, we're going to see what all these correspond to. And so that just means water. So the entire image here is being classified as water, which to me actually looks like a mistake. Find a better example. So we've got some streets and houses. Here's the corresponding color map, some grass. There's trees, road, non-flooded. I want to just find all of the things that say building flooded or road flooded. And if I see either of those things in the label, I'm going to classify the image as flooded. I have a function that'll do that. And we're going to use this to pass over our entire data set. I have this wildcard in my color mask path. The name of the image is the ID, which I put in here. And in order to do this matching, I actually had to get all of the pixel values and then check if these pixel values corresponding to the right labels. So we have 255.00 for building flooded and 160, 150, and 20 for road flooded. So if I see either of those in the image, I know that it's flooded and I'll return that label. Otherwise, I'll just return that it's not a flooded image. Import TQDM for our progress bar. Now while this is running, I'm going to keep writing some code and I'm going to create a little helper lambda function for our captions. When we're training clip or using clip for making inference, this is a satellite image, so I think that'll help clip get a little bit of context of what our data set is. Let's look at these image labels. Most of the labeled data is non-flooded and it's almost 10 to 1. There are certain strategies which I could use to deal with this type of imbalance, but I'm not going to do any of that. Now I'll apply those captions and create a captions list. And next I want to look at some examples in our data. So I'm going to create a mask and I'm going to say numpy.array, which by the way, I'll have to import. Here I'm going to put in my captions. I want all the indexes where that equals, instead of the non-flooded, I'm more interested in the flooded examples to start with. That's going to be my mask and we'll see what that looks like. If I look at the sum, I want to make sure this is non-zero. So these are my 182 positive classes. And now to get the indexes of these, I can say numpy.where and then just m. And this is all the places where this is true. So let's pick some of these, say at random.choice. Let's grab 5 of these. I need to open that image. This one is an array itself. To come in here and take the 0th element there, resize this. Maybe 600 by 500 would be good. This looks pretty good. And these are definitely flooded images. To make sure everything's working well, I also want to plot some non-flooded images. And I need to say equals in that way. Great, so these are some examples of non-flooded land. Next, I want to unify these captions and images into a single data structure. And so to do that, I'm going to create something called a record, and in here I'll have a caption, and I'll also have an image for that. And I want this to be a data class. Data is going to be a list of these records. I'll iterate over them. and I'll zip together these captions and these images. It'll be in whatever order that these happen to be read when I did that with pathlib, in numerical order with 1s and then 8s up here. But I want to randomize all this because I don't want to feed these into my neural network and be updating my weights in like a certain order. I want it to be random. So in order to do that, I'm just going to shuffle all this around. From random import shuffle the data. And once I do this, it'll shuffle it in place, so it'll return none. And now if I look at my data in this cell right here, we're going to see it's all shuffled, it's all random. And we can confirm it's the length that we expect. We're seeing that it is 1,445 samples. Now we're going to start using PyTorch, and I'll import torch like this. And on my MacBook, I can run this piece of code in order to set the device. And I want to make sure I'm using MPS device. This is my GPU. Next, I'm going to load the clip model using transformers. So from the Hugging Face transformers library, I'm going to import clip model right here and clip processor. This clip processor is able to process both images and text. Now I can go ahead and load them on my computer using this code. The first time you run this, it'll have to pull these models onto your computer and stores them in the cache directory, as in this one. Now let's test this model out. Just going to grab the first 3 captions and the first 3 images. We're going to be padding these, and we're going to be using PyTorch, and I'll explain what those mean when we're looking at the data. So now I have some inputs. I've called these inputs because these are the things that we're feeding into the neural network, either to do inference or to do training. These inputs have 3 fields. There's input IDs, attention mask, and pixel values. I'm honestly not sure what the attention mask is doing, but I know that the input IDs correspond to the text. That's how the text is tokenized. And then the pixel values are for the images, and these are just the pixel values of the images. I'll look at the input IDs, and I could look at the shape. 3 because we had 3 records, and each record has 14 items in it. Also look at the inputs for the pixel values, and say I was to just get like the first one. This is going to be for a single image, and what I could do is look at the shape of that. And we can see that there's 3 layers, so red, green, and blue, and then in each layer we've got a pixel array of 224 by 224. We're going to evaluate the model prior to fine-tuning it. And to do that, I've got a big chunk of code right here, but I'm not ready to run this yet. And what I want to do is, since we're in a Jupyter notebook, grab this, play around with just this chunk of code. After we've done one loop, I just want to break out of it and see what we have here. And I want to do it in batches of 8. So let's run this. I'm reporting that I'm using this MPS device. After running that line, I send the model to that device. But you notice above that, I actually set the model to evaluation mode. And this tells it, like, we're not training, don't compute gradients. We don't need to worry about computing gradients. And that's because we're not doing any training, like gradient descent. We don't need those right now. What we do need to do is feed in these inputs into our model. And after processing them, which should look really familiar, we just were playing around with this, and we've been doing this in previous videos. What I do is I take each of those values and I actually send them to the GPU with this dictionary comprehension, feed them into the model, unpacks these inputs, tokenized text values, pixel values that we were just playing around with, and then we get our outputs. And this is the result of our model. So these are not the embeddings, but just the model results. I'm looking at this logits per image. What this gives me is the text image similarity score. And we'll examine this right now. By the way, this finished running because this TQDM loop was inaccurate since I broke out of it. So now we can examine some of the data from this loop right before we broke out of it. So for example, the batch, we should see the batch of the first iteration. If I look at the batch, these are like the first 8 images which we fed in. I could also look at this logits per image, which I'm really interested in. And here I can see for each of these 8 images that we fed in, what I'm doing is I'm getting the similarity score, in this case with the first label, and in this case with the second label. And then this is the next image, and this is the similarity score with the first label and with the second label. And what are these labels? I define them right here: a satellite image of a flooded area and a non-flooded area. And if I look where these are used, I'm using these in the preprocessor. So these are part of the inputs to our model. In fact, if I look at the inputs, and these would have been the inputs that were fed in, and let's say I look at the pixel values and I want to get the shape of those, so I can see that there's 8 samples being fed in here. But now if I look at the inputs of the input IDs, this is the text derived data, the tokenized data, there's only 2. And each of them have 14 tokens, and that's because there's only 2 labels. So for each of those 2 labels, I'm looking at all of these pixel values, and that's how this is produced. And so these are the similarity scores I'm interested in. And whatever is higher in each of these cases has a higher similarity score, and that is our predicted label. We look at the argmax. This is going to get me a list of 1s and 0s. And so to get the appropriate labels, remember I have these labels, and what I want to do is simply just get like the label of the index for the index in pred index. Sorry, I mean the index like that. Then lastly, I have access to these captions, and these are the 8 captions corresponding to my training images. I'll just remind you up here, these are the captions. I'm unpacking them from my batch. And so I can simply compare these captions to these labels. And what I can do is these captions are already an NumPy array. So I just have to be like, are these equal to my labels? And so I'll grab this guy here and I'll cast this as a NumPy array so that everyone's speaking the same language here. And we can see that some of these are true, some of these are false. These are things that didn't match. And so I think I've shown you enough of what's happening in this loop for you to understand this last step where I just kind of add all of these up. I fetch the item and then I add that to the correct labels, and I'm keeping track of all the total correct labels and then all of the total like attempts, and then we'll be able to get the accuracy. So if I come down here when we actually run this, I'm returning actually the correct divided by the total in order to get that accuracy that I'm looking for. Without further delay, let's do this. Accuracy before fine tuning. We'll kick that off right now. This finished in 4 minutes, and the accuracy before training is just below 70%. Now, while this was running, I thought I wanted to talk more about these logits per image, because you might be wondering what these are. I told you they're the text image similarity score, but you'll notice that they're not actually in the right range for the cosine similarity. We'd expect them to be between -1 and +1, but they're far different. So why is this happening? Well, I looked up the clip model documentation, and if I scroll down to this logits per image object, it says it's the scaled dot product between image embeds and text embeds. This represents the text image similarity scores. So it is using the dot product, which is the same way that the cosine similarity is calculated, but it's scaling it somehow. So we can't exactly interpret this as a cosine similarity. However, I do believe that these would always give you the same result as doing the cosine similarity when it comes to actually picking out the one with the higher score, so comparing these two. Now, what we can do is use the softmax function in order to convert these into probabilities. From scipy.special, and I'm going to import it. Once we have that, we're going to use it, and let's use it on the logits per image, and I'll try and just feed in the first element. Maybe if I say to CPU, all right, that worked. And look, these are valid probabilities. If you add these up, they add up to 1. And so we can interpret this as saying the first label has a 28% chance of being true, and the second label has a 71% chance of being true, according to the clip model. By the way, this softmax function will take any set of numbers and convert them into a valid probability, as in probabilities for each like index that add up to 1. So for example, if I took something like 12, maybe 4, and then I don't know, 3 and 1, and I run the softmax on those, now all of these will add up to 1. I could say .sum, and we're just going to get 1. They're in a valid probability space. So in the loop, I have this kind of commented out code, which does look at the softmax, and it's just indicating that we could get the label probabilities that way. But in any case, we have a 70% accuracy. So Clip is able to identify 70% of these satellite images correctly. And you'll remember how our images were distributed. Most of them were non-flooded. It was like 80% non-flooded images. So this is actually performing worse than if you just randomly guessed that every image is non-flooded. And here is the big gnarly chunk of code that we're going to use to fine-tune our model. I'll need to import a couple additional things. One is just time, because I want to track how long our epochs of training take. And next I need this atom w optimizer from torch.optim all import atom w. And let's start by looking at that atom w docstring. One thing we're going to be doing is explicitly setting a learning rate. This is something you might want to play with if you're trying to fine tune your data set, as well as the other parameters that we have available to us. This is really similar to gradient descent. It uses the same idea. Now, in order to understand a little bit what's happening here, I'm going to use the same trick as before, and I'm just going to break out of this after we've done one batch, and then we'll sort of observe some of these variables, how they look after the first batch. I also need to break here, but I'll do that after printing sort of this epoch summary metric, whatever, and I'm going to need to remove both of these break conditions later when we actually want to train or fine-tune our model. And I'll start by just sort of walking through what's happening here. We're defining our processor and our model, and whereas before I set it to eval mode, now I'm setting our model to train mode. I'm also making sure that it's sent to the proper device so that I can do this on my GPU. I want to do 5 epochs, so that's 5 complete passes over our full training data set. And during each of those epochs, I'm just going to batch it in sizes of 32. So I'll only look at 32 images at a time and corresponding captions for those images. All of this code should look pretty familiar. It's the same thing we were doing to eval our model, but now we're going to be using those outputs to update the model parameters. I'm looking at the logits per image. You can interpret this as like the similarity score for all of the images, but what are they being compared to? Well, they're being compared to the text. But we also are doing the same thing with the text. We're comparing the similarity of all the text with all of the images. And this is the contrastive learning, because we expect some of these to match, but then in fact one should match for sure, and then the rest we don't expect to match. And that's being encoded in these matrices. So let's look at those. And after we look at these, I'll continue to move through this and we'll talk about what's happening here. So logits per image now looks a lot bigger than before. That's because for each image, which is like a row in here, we're comparing with each piece of text. And so if I look at the logits per text, it's the same thing, but it's the transpose of that. Because now for each piece of text, I'm looking at all of the images. So what that means is this second index here compares the first image with the second caption, and it's 24.62. And so down here, I want to see the second caption comparing to the first image, which is the same piece of data, and so it's the same number, 24.62. I could also, I don't know, say grab anything and transpose it. So in the top right corner, we have 24.62, and that's going to match the bottom left, 24.62. So these are the pieces of data we're thinking about as we continue to look up here. These represent the cosine similarities like we were talking about earlier. The first thing we're doing is a line that really confused me when I was thinking about how this fine-tuning is happening, because it seems so arbitrary. We're arranging a bunch of numbers. We're just labeling the indices. This is just going to produce an array that's like the index of each label. I'll show you what I mean here. We had 32, that was our batch. So if I run this, we're just getting a list of numbers from 0 to 31. And then what we're doing is we're taking those labels and we're computing the cross entropy with these logits. And why this makes sense is really obvious when we look at the documentation for cross entropy from Torch. So I've pulled that up here, and our inputs, the first argument we want to put in is the predicted unnormalized logits. And then next, we're going to put in the target, the ground truth class indices. And that's what we've done. We have all of these class indices for the ground truth labels. This will produce a loss for the image, like how badly the images were matched, and for the text, how badly the text were matched. And these are different things which we can average out to get like a general idea of the loss of how well our model's doing. So when we do this in a batch, we're going to be kind of adding to this epoch loss. And then I'm going to be adding these epoch losses together right here into a list so we can like visualize our loss curve over time. And what we want to do is see this loss decreasing as we update the model parameters. We want to see the cross entropy getting lower, which indicates a better fit between the labels and the predicted labels. This last step here is the actual thing that's updating our model parameters. Call this backward method, which calculates all of the gradients. We're calculating the rate of change of the loss with respect to changing our model parameters. Then what we do is actually do the model parameter update. So we take optimizer.step in order to update all of these parameters in our model. Lastly, we want to zero out all the gradients. So if we don't do this, and that's say commented out, every time we call this loss.backwards, it's going to add the new gradients with respect to the most recent batch to all of the previous ones, and it'll just keep like adding these on top of each other. With PyTorch, we need to explicitly zero those out, and I want to do that after I make a step. You'll also see sometimes like that being done, say, I don't know, up here before everything's done. Before we call backward, and that works too, but this is just how I've done it. And then all of the remaining code for logging, keeping an eye on my loss. Remove these break statements and let's go. After the first batch has completed, we're estimating that it'll take 8 minutes, but this is just for the first epoch, and I'm doing 5 epochs. So this could take up to 40 minutes to complete. I can see our model's finished training, and now what I want to do is plot the epoch losses. And here's what our training looks like. So if we continue to train, we might see that our loss improves, or we might see that we start kind of oscillating around some minimum. I'm happy to stop here because I can see that we've achieved a great loss and we're starting to level off. What I'm going to do is save this model so that we don't have to retrain it later. I've got a models folder, and here's where I'm saved my previous versions. So I'm just going to delete these and we'll resave them right now. You can see them being created, and these are actually folders, and they have a config in here and then a tensors object, and this will be all the parameters for our model. Now let's evaluate our saved model on some data, see how it does for accuracy. So I can right click this and say copy into new window, and this will open up the same instance, the same runtime for me in a new window. I'm going to scroll up to where I define my evaluate function, so I can just copy this, paste this in, leave the batch size to default, and we're going to use our new model. And so let's evaluate our model on all of this data. Now, what is this data? This is all of the data that I just trained the model on. So we would expect this to be pretty high, right? I mean, this is all the data that we've just been fitting our model on. And we've been looking at the loss, and that's been going down. That evaluation took 5.5 minutes. And our accuracy after training is perfect. We're getting all of our samples correct. Now this probably indicates some overfitting, which means it might not generalize that well to unseen data. But in any case, it's not fair to judge the accuracy of our model on the training data. We want to judge that on some test set of data that's been withheld from training. So now the plan is to load some test data and evaluate the model on that. And I want to evaluate the fine-tuned model and the non-fine-tuned model, and we can really get a definitive comparison of accuracy, pre and post fine-tuning. I'm going to be loading these test image paths, and then I'm creating a new color mask, or rather I'm changing the path. So we're going to be looking at the test set now. And I'll run this just to quickly generate some labels for our data and create these test captions, like satellite image of flooded land or a satellite image of non-flooded land. And then I'll paste in a little code block just so we can sort of sanity check our work. And I'll do the same thing for the other caption. So here's some labels of flooded land, barely flooded, a flooded road right here. And down here, we'll have some examples of non-flooded. Some of these are tricky because there's a lot of water in this one. So this is going to be a hard one for the model to understand. I'm going to redefine our evaluate function, and I'm adding one thing in here. I want to keep track of all the misclassified images, and I'm doing that with this line. So I look at all the correct labels and I just iterate over the items in the batch. These are all of our individual images in our batch of images we're using to train. And if for that batch we know that that label is not correct, then I want to include that in our misclassified images. Use this list comprehension to create our test data, and then we're going to batch over all of these records. Just keeping track of these misclassified images so we can see some examples at the end of this of what the model failed to work for. Start with the standard clip model and evaluate it. So this is going to be before fine-tuning. I'm going to reload it from the version we have cached on our system, and then I'm going to run this evaluate function, which is this guy here. So we'll get the misclassified images, we'll get the accuracy, and I'll go ahead and print that. I'll get that running now. Do the same thing for the fine-tuned model. So I can use the same code here, but instead of loading it from the cached version, which we pulled from Hugging Face, we're going to use the version that we fine-tuned and saved on our system. Once that's loaded, I'll call the same 2 lines as above, but now I'll save these as fine-tuned accuracy and misclassified images, giving us the final result of all of our work right here in this cell. There's a lot less test data, so it's evaluating a lot quicker. I'm expecting this to be about 70% because that's the accuracy we got on the training set when we evaluated it on the base model. And here we're seeing an accuracy of just under 70%. Now we've started doing this for our pre-trained fine-tuned model. We're almost ready. And here we go. We have an accuracy of 98%. So let's look at the actual number of misclassified images. Base clip misclassified images. By the way, I should contextualize this with the length of the test data itself, 450. Now let's see how many misclassified images we get with the fine-tuned model. And here we're only getting 7. So let's see what those look like. I can iterate over them in this way and display them. Same aspect ratio. So this one was misclassified as a flood, whereas this is just kind of like a water catch river thing. Same with this one. Pretty easy to see why the model would not know that that's a flood. This one's a river. This one definitely looks like flooded land. So you see the pattern right now. In general, these are going to be really tough. But then this one, maybe we'd think, okay, no, this should be classified correctly. And so maybe there's something in the model that we can do to catch cases like this. Observability into the reason why models are failing and really connect this data and these kind of abstract code and numbers to actually like what is actually happening in the model. Like what am I actually misclassifying? Let's look at it like with my eyes as a human and think about it. That stuff's really important. But this is the end, and I really just want to leave us with the final view right here and just showing like the effectiveness of Clip being able to modify its parameters with PyTorch using this fine-tuning method and just how amazingly well that worked. And for me, this was one of the like, oh shit moments when this actually worked. I was very excited. That brings us to the end of my series on multimodal embeddings. I want to talk about some implications of trying to do this in a real world setting. Before I talk about those considerations, I'd appreciate it if you gave this video a like if you enjoyed it and consider subscribing. These actions really support me and this channel and what I'm trying to do here. And if you like my YouTube stuff, I think you'll enjoy what I'm creating over on Patreon. So you could check that out and you could sign up for my newsletter for free. It's basically just a link to the YouTube video that I made that week. Now, this set of demos I've done on multimodal embeddings, it feels like one of the coolest things I've ever done with open source ML on my machine. There was also a lot of difficulty, like I was getting memory overflow errors at certain points, and I had to learn a lot like about PyTorch, or at least enough to be able to sort of explain my way through it. In this space of machine learning and ML ops and data engineering, there's so much to understand that it's really, really hard to know like from first principles for absolutely everything. And at some point, I find I have to sacrifice like a core understanding of something to be able to understand a different aspect of it better, or get like a broader net around the whole area and be able to kind of do that full stack that I'm advertising and that I'm trying to teach. So bringing this all back to some point, you know, on one hand, this was really cool and exciting and felt like just pure magic. But on the other hand, I do realize that this is only like scratching the surface of what we'd actually need to do to make this type of system practical in the real world. First of all, we have a pretty small set of training data. And so even though the model that we created works really well on this particular data set, who's to say that it's going to work well on a different data set? Like, what if our satellite is taking images from farther up? Or what if it's like a different satellite that renders images differently? There's going to be some bias to deal with. Consider this case. Let's say we have 2 different satellites taking images of 2 different events. And one of these events is really bad and there's tons of flooding. And let's say like 90% of the images are of flooded area. And let's say for the other satellite, we're taking images and these images look different. Like they have different average pixel values, for example. Or maybe they have different effects around the borders, like they're not uniform for some reason. There's some bias in there. And then let's say that event that's happening, only like 30% of the images are flooded. So now our model is going to learn that Okay, well, when we're seeing images from that one satellite, chances are that those ones are going to have a lot more flooding. And that's nothing to do with the content of the picture, but it's a bias introduced by the mechanism by which the images are taken, like those average pixel densities. So we have to do things to correct for those biases when we're training our models. And this is really hard. It involves like iterating on models and being thoughtful about ways that bias is coming into our data set. And so that's more on the training aspect and the modeling aspect. But how about just getting that data available to us? We need a whole system for that. And this is where data engineering and ML ops comes into play. We've got some data coming upstream and we have to like capture that, store it somewhere in an appropriate format. So this could be like cloud storage, like S3 or Google Storage. And then we need a system for retrieving those images from storage, doing inference, calling our model. We need to have enough compute so that that's working. If those need GPUs, we need to have GPUs provisioned for that purpose. And then we need to return our response to the user. And maybe we need some sort of front end or like an API set up, or maybe some sort of dashboard for some observability into how this is going. And that's a model that's not even updating. Now you want to have an online model that's like updating with fresh satellite image data. So how do we do that effectively? And how do we make sure that, you know, the new model that we train and deploy automatically isn't crap? So we need to be able to look at those loss curves and maybe like see some examples of misclassified images and just kind of like have our sanity check that everything's working well. And this is very much in the ML ops realm. But anyways, my comment section is open if you have ideas on future topics for videos. I learned a lot doing this series, and I hope that you learned a lot by following along. Thank you so much for watching. I'll see you in the next one, and namaste.